All right, so since we are talking about things we're thinking of as orderings, it makes sense to talk about, or it's interesting to talk about minimal and maximal elements. And there are a few different senses in which we can mean these things. Basically, because partial orders are a lot more diverse than total orders, there are a couple different definitions that you can give that will mean, in general, slightly different things. So let's start with, say an element x is maximal if there is no y with x strictly less than y. So it's maximal if there's nothing bigger than it. And say x is minimal if, analogously, there is nothing smaller than it. If there is no z with z strictly less than x. But let's point out that this is sort of, if you have some intuition for relative maxes and mins versus absolute maxes and mins, maybe from your calculus days, this corresponds to a relative max slash min. And we will have a different name for an absolute max or min. But notice that because you're saying there's no y, for example, that's strictly larger than x, since this is a partial order, there can be things going off in all directions. So there can be a number of different things that have nothing bigger than them. So we can see that in these examples. Let's go ahead and label, well, actually, yeah, let me first give you the definitions of absolute maxes and mins. So say x is the greatest element if everything is less than or equal to it. And similarly, x is the least element if x is less than or equal to z for all z. And these are the analogs of absolute max and min. And again, you can see the difference is that these definitions are saying something more specifically about x, and these definitions are saying something about generally all elements of the set. So let's look at these two examples and let's label what kind of extreme elements we have in each. So for our linear order, on this side, the situation is fairly simple. 4 is maximal. It is also the greatest element. Because you can see there is nothing bigger than 4. It has no line coming up top. And it does have a line down to every other element. So the first thing, that there's no line going up, means that it's maximal. And the second thing, meaning that it connects downwards, connects downwards to every other element, means that it is the greatest element. And similarly, on the other side, 1 is minimal, because there is no line coming down out of it. It is also the least element, because every other element is greater than it. So that is the simple case. This other case is slightly more complicated. So essentially, this reasoning we were saying over here is the same about maximal elements, If there's no line coming up from a certain vertex, then it is maximal. But in this case, we have a bunch of them. So 9 is maximal, 6 is maximal, 8 is maximal, 10 is maximal, and 7 is maximal. These are just all the vertices that have no line coming upwards out of them, which is to say all the points that have nothing greater than them. But you can see also that in this case, there is no greatest element. Because there is no element that has a line down to everything else. For example, 9 and 6, there is nothing that is above both of these things. So in general, there can be no greatest element. On the other side, 1 is minimal because there is no line coming down out of it. In fact, it's the only minimal element, and it does have a line up to every other element, etc. So it is also the least element. So in general, all of these things can exist in all of these combinations. Greatest and least elements might exist or they might not. Maximal and minimal elements might exist and they might not. One thing you can say, which is maybe a good practice problem, is that maximal and minimal elements can come in any quantity, but greatest and least elements are unique if they exist. So if you have a greatest element, you will have exactly one of them. And if you have a least element, you will have exactly one of them as well. So that is what we are talking about specific elements. We are also interested in talking about subsets. So let B be a subset of our partially ordered set. An upper bound of B is an element U such that every element of B is less than or equal to U. So it's an upper bound in the sense that it is greater than or equal to every element of this subset. And similarly, a lower bound of B is an element L in A such that L is less than or equal to every element of B. And furthermore, we can add the least upper bound again, if it exists, is the least element of the set of upper bounds. And the greatest lower bound is the greatest element of the set of lower bounds. So all of these things as well may or may not exist. A subset may have an upper bound or it may not. Even if an upper bound exists, there may or may not be a least upper bound. And similarly with lower bounds. So it's good to try and come up with examples of all of those combinations. So let's look at this example again. So what about the subset 1, 2, and 5? Does this have an upper bound? Well, that's these elements. And we can see that 10 up here is greater than or equal to all of them. So this has an upper bound. In fact, this is the only upper bound, so it is also the least upper bound. What about the set 3, 2, and 5? So that's this set. You can see from the Hasse diagram that there is nothing that bounds all three of these from above. So it has no upper bound. What about the subset 6 and 10? Does this have any lower bounds? It does. So 6 and 10, what are the elements that are less than both of them? Well, 2 is less than both of them. And 1, in particular, since it's less than 2, is less than both of them. And those are the only things. So it has lower bounds. 2 and 1. So 2 is the greatest lower bound. So can we come up with an example in this case where there is a lower bound but no greatest lower bound, or an upper bound but no least upper bound? In fact, in this case, we cannot, because there's a nice interpretation though, which we know will exist. So in general, if we consider the positive integers with divisibility, then the least upper bound is simply the least common multiple of a bunch of numbers. And the greatest lower bound is the greatest common divisor of some numbers. So in this partially ordered set, every subset, maybe I should say every finite subset has a least upper bound and a greatest lower bound. But in general, in a general partially ordered set, it is certainly possible to have a subset which has an upper bound but no least upper bound. And that's a good exercise to go and try and find an example for yourself.